Ever open Yelp, Tinder, or Google Maps, and boom, there's a perfect list of spots right around the corner. It feels like magic, but it's actually a masterclass in geospatial engineering and scaling. Today, we're diving into this explainer to unpack the massive system design behind how these proximity services instantly find places near you. Let's see exactly how this architecture is built.
Here's our roadmap for this explainer. We'll start with the proximity problem. Look at the geospatial indexing core, compare GeoHash and QuadTree, tackle scaling with replicas or sharding, dive into strategic caching layers, and wrap up with some tricky production edge cases.
All right, section 1, the proximity problem. Finding nearby places sounds incredibly simple on the surface, right? But at a global scale, with hundreds of millions of locations, it gets super complex.
Now, you might be wondering, why can't we just use a standard SQL query to search a 2D radius? I mean, why not just draw a circle using a simple 2D intersect on your latitude and longitude? Well, standard database indexes are really only optimized for one dimension at a time. If you query lat and long ranges together, the database has to pull two massive datasets and perform a highly inefficient intersect. We're talking full table scans or incredibly slow index merges. Throw 100 million users at that, and your database will literally melt down.
Which brings us to section 2, the geospatial indexing core. To avoid that database nightmare, architects had to completely rethink them.
The industry standard fix is geospatial indexing. The whole trick here is taking two-dimensional coordinate data and mapping it into a single one-dimensional format. By doing that, we can use standard, blazing fast database lookups. So instead of calculating a massive radius on the fly, the system just looks up a specific grid or bucket that you happen to be standing right inside of.
When it comes to actually making these grids, industry leaders rely on three primary algorithms. First, there's GeoHash, which shrinks 2D data into a 1D base 32 string. Next is QuadTree, which is an in-memory tree that recursively divides the map into 4 quadrants. And finally, Google S2, famously used by Google Maps and Tinder, which maps a 3D sphere to a 1D index using a really cool mathematical concept called a Hilbert curve. That basically ensures points that are close on a map stay close in the index.
Moving right along to section 3, GeoHash versus QuadTree.
Since Google S2 can be a bit mathematically heavy, let's look at the ultimate architectural showdown for most services, GeoHash versus QuadTree. To make GeoHash instantly click, just think of it like a zip code. A string like 9Q8ZN represents a specific grid. Add another character to make it a 6-character string, and you zoom in on a much smaller grid, maybe just a single city block. It's super elegant because finding nearby businesses literally just means searching for database rows that share that exact same string prefix.
So how do they compare? Well, GeoHash gives you incredibly low memory and CPU overhead. If a restaurant opens up, you just insert a single database row. Easy. QuadTree, on the other hand, is dynamic. It builds an in-memory tree that adjusts perfectly to population density. Tiny grids for New York City, huge ones for the Sahara. But here's the catch. A quad tree for 200 million businesses eats up about 1.71 gigabytes of memory. While that totally fits on a modern server, building that tree at server startup takes serious CPU time and can massively complicate deployments. That said, if you absolutely need to find the exact k-nearest spots regardless of radius, QuadTree is the undisputed champion.
Let's hit section 4, scaling. Replicas or sharding.
Once you've picked your algorithm, you've got to scale it to handle thousands of queries per second, especially during peak meal times. Now, when engineers hear scale, the immediate reaction is usually database sharding. But hold up, sharding requires really complex application logic to route data. And remember that 1.71 gigabyte memory footprint? Even with GeoHash, the entire spatial index is surprisingly small. It easily fits into the working memory of a standard database server. So, adding read replicas is actually the clear winner here. You just copy the data to multiple replicas to share the heavy read load. It's operationally way simpler and incredibly effective.
Next is section 5, strategic caching layers. Time to push this system speed to the absolute limit.
We do that by adding in-memory caching with something like Redis. And the really clever move here is splitting the cache in two. Why? Because the spatial index and the business details change at totally different rates. Your first cache maps a GeoHash grid string to a simple list of business IDs. For 200 million businesses, that takes just 5 gigabytes of memory. Then, your second cache takes those IDs and hydrates them, fetching the bulky data like restaurant names, addresses, and photos. By separating the fast grid lookup from the heavy object payload, your memory footprint stays optimized and response times stay lightning fast.
But keeping a cache updated is notoriously brutal. So here is a genius trick. Instead of wrestling with complex, multi-threaded, real-time cache invalidation, system designers solve the engineering problem with a business rule. They simply have users agree that profile updates take effect the next day. This lets the system batch all additions, deletions, and edits into a highly efficient nightly cron job. You completely sidestep concurrency headaches, save massive amounts of system resources, and guarantee rock-solid stability during the daytime rush.
Finally, Section 6, Production Edge Cases. Because let's be real, theory is one thing, but production is messy.
What actually happens if a restaurant sits right on the edge of a grid? This is a major boundary issue. With GeoHash, the longer the shared prefix, the closer two places are. But the reverse isn't always true. You could have two places literally meters apart, but if they sit on opposite sides of the equator, their geohashes share absolutely 0 characters. If your system only searches the current grid, you'd completely miss the amazing bakery right across the street just because it falls into a different geohash bucket. Wild, right?
So here's the step-by-step tutorial on how that's handled in production. First, you just acknowledge the boundary flaw exists. Second, and this is the magic part, your application logic mathematically calculates the 8 neighboring geohash grids in constant time. Third, you hit the cache for your current grid plus all 8 surrounding neighbors, grab all those businesses, compute the exact distances, and filter them locally. And fourth, if you happen to be in an empty desert and don't get enough results, the system dynamically expands the search radius by dropping the last digit of the geohash, geometrically increasing the search area. Boom!
We've looked at an incredibly robust architecture for static businesses today. But I want to leave you with this provocative thought. How would you evolve this exact system to handle a ride-sharing app? Instead of a static restaurant, you now have millions of cars updating their location every single second. How does that change your quad tree build times, your caching strategy, or your database rights? Think about it, and let it push your system design skills to the absolute limit. Thanks for diving into this explainer with me. Keep exploring, and I'll catch you next time.